Hello everyone, my name's Simon Michaux. I'm an Associate Professor of the Geological Survey of Finland. The work I'm going to show you today is a quick summary of the work I've been doing over the last few years. I'm not only going to show you the work on the green transition, how it will struggle in its current form, but I've actually started to put together a counter plan that might work, and I call it the purple transition. So today's talk is black swans, white swans, and the purple transition, and where we will be going. First, I asked, what is required to phase out fossil fuels? How big is the existing fossil fuel system, and what do fossil fuels actually do for us? These basic questions have been missing from the European lexicon when I arrived from Australia. What are the primary tasks of the green transition? What does wind and solar need to function in large networks? What we're really asking is how big should the power buffer needs to be to manage intermittent supply? What quantity of metal is needed to construct a complete non-fossil fuel system as it is now, or actually in the year 2018? And can recycling supply this? And can mining supply this? And if the green transition won't work, if that's the case, what might? So then I'm going to present the purple transition in the latter part of the presentation, which is a reimagined commodity sector with 4 foundation technologies around that, 3 of which are already in commercial development. Okay, and the relevancy of this picture will be apparent when we get to the end. The basic question is this: will this work for everyone the way we plan? Will it work? How do we continue to resource what we see in this picture? You know, these really big cities that chew a lot of energy. So I put together this study. Now the study is actually in 3 parts, and you're looking at the first part. It's a map for the year 2018 of what actually happened. What were the physical tasks done industrially by fossil fuels in the calendar year 2018? Once that was quantified, what was the true scope of useful work done where each system, for example, an internal combustion engine, has an energy efficiency of, between true work done and energy consumed? And if we were to assemble a whole series of non-fossil fuel technologies, electric vehicles, hydrogen fuel cells, wind turbines, what have you, how many will we need to do the same useful work? And a lot of them require electrical power to run. So how much electrical power will we need to expand the power grid by? And given an energy mix proposed by the IEA for 2050, where wind and solar take the majority of the power mix, how many non-fossil fuel power stations are needed? The elephant in the room is the intermittent power storage required for wind and solar was much, much, much larger than any of the conventional strategic planning I've seen allows for. More on that later. Right. So what we need is an extra 48,939.8 terawatt hours of capacity in addition to our existing non-fossil fuel systems. Sum that all together, the new power grid will be 58 petawatt hours for the year. These are the tasks as split up. The existing electricity demand is black, but we've got all these new tasks, and we'll go through what we mean by those. But the charging the electric vehicles and their batteries is only a small part of what we need to do if we were to go this way. Whereas most of the actual research groups that I was actually part of for the last 7 or 8 years would only look at batteries and batteries for passenger cars. And it turns out that's actually a very, very small part of the system. All right, so we've got on this column here the what power was actually consumed in 2018. And oil, gas, and coal are the white squares, which we're going to phase out, but the coloured squares down the bottom are the non-fossil fuel power systems which apparently we're allowed to use. And the column on the right is the additional electrical power that we've got to bring in. to do this job. So we're going to knock out oil, gas, and coal electrical power generation, charging the EV fleet, producing hydrogen for various tasks, steel production in a hydrogen atmosphere. We're going to produce ammonia for various tasks and the heating of buildings. And so we sum all that up together, and that's how we get our 58,468 terawatt hours for annual electrical capacity. So what we want to do is bring in a power grid that is substantially larger than the one we've got already, using electrical power that's not as effective. And at the moment is more expensive, but it's actually not as effective in terms of real physical work done. So the old system's on the left and the green transition is on the right. Okay, so now we want to bring in, this is the global, this is the world map, that's a composite of satellite imagery where they've taken away the clouds and they've stitched it all together. So this is the global system. So 1.4 billion vehicles traveled 16 trillion kilometers in the year 2018. Okay, what was interesting when I first started this work was that basic question, how many vehicles were in the global fleet, was really hard to answer. There were studies to show it for the United States and for Europe and for China, but no one had stitched them all together. So I had to do it. And then I had to actually estimate the actual distance traveled. And it was really strange. How are we going to know how many batteries we need to make if we can't answer those basic questions? And it really surprised me this information wasn't available. Right, so that's the amount of power that we want to bring on additionally. Using the energy mix proposed by the IEA, we need 800,000 new power stations of average size. The trouble is, the existing power fleet's around 46,000. So we're talking about a power grid more than 10 times the size of the existing fleet. If you were to take out a single fossil coal-fired power station, how many solar panels do you think you need to replace it? The power storage buffer, which I'm going to talk about shortly, is associated with wind and solar only, which represent about 70% of the energy mix now. Conventional thinking believes that this power buffer is only 5 to 7 hours. And where this number comes from is this is the Net Zero America study done by Princeton University. Very nice piece of work, if I might say so. Very well presented. Okay, so here's how they've come to that number. So this is a power simulation over 120 odd days. And each day and night, we have a, sorry, that'd be hours along the x-axis. Each day and night has a peak and a trough. During the day it peaks, and during the night there is a trough. The solid line is the demand load. Sometimes supply exceeds demand, and sometimes the other way around. If we were to catch the times where it exceeds demand and keep it, and then release it for when demand exceeds supply, we only need to keep it for a couple of days. And the calculations done for the United States, this is a study with the United States, they only needed 5 to 7 hours to manage that switching problem. And that work is pretty good, and it's true. What it does not look at is the long-term seasonal variations, for example, the difference between summer and winter. So it's not that this study is wrong, it's that they didn't include certain things in their calculations. So the way we actually sort of balance power, this is Europe in 2021. Each nation state, no one actually generates exactly what they need. Every nation either produces too much or too little, and then they trade it. And so all networks are balanced and buffered off against something else. And if we want more electrical power, we used to burn more fossil fuels, gas in particular, to balance things out. In winter, if we need more heat, then we burn more gas. It really was as simple as that. Most existing renewable power grids are balanced from fossil fuel systems in this manner. We've never had to run a really large renewable network in a self-sufficient manner where it's internally stable over like a full year cycle of seasons. So let's look at that. This is solar radiation for Germany. in 2015. And you might notice in winter, the solar radiance is much less than summer. But if this chart now represented 38% of the global energy mix, and our power requires the same current, same voltage, same frequency to come out of the power socket in a sinusoidally clean fashion, clean power. So it's got to be the same, which means this power grid would have to smooth to a straight line. Everything above that dotted line would have to be captured and stored. And then below that dotted line, you'd have to actually source power from somewhere else. And the grey squares here, that would be the buffer. So the power buffer would need to collect excess power over 6 months, store it for about 6 months, and then release it over a period of time 6 months after that. Right, so that little red square there is 28 days capacity, and I found a reference for that, and that's what I've been using for my calculations until reasonably recently. I thought it was a conservative estimate after sort of looking at these sorts of charts. It turns out the trolls on Twitter took umbrage to this. So now I use 4 calculations. So there's 28 days, 48 hours plus 10%, and that's our 6 hours or 5 to 7 hours right there. And the fourth reference I found was 12 weeks, which actually would fill up most of this grey. Here is a case study of a system in Spain. It's a concentrated solar system. It's not a standalone, but if it was, so we've got 2 months, it's June and November, summer and winter. If it was a standalone system, it would be a 670 watt constant for baseload generation. The dark orange is what would have to come from power storage. Now, what this study does, and this author, Ewan Mearns, does excellent work. I can recommend him. What they found was for the month of November, you needed 16.2 days just for the month of November, and you'd have to store it for something like 4 to 6 months. So this blows out the whole thing of 5 to 7 hours right there. Wind is highly variable. So this is a meterage in November 2015. They did a study in 2014 with the UK Parliament, and they had some storms come in that year, and the power production was so erratic it couldn't be predicted. So this chart for 2015 is actually a bit more civilized. But imagine if this chart represented 38% of global energy mix. And so look how unstable that is. And if we had to actually sort of force that into a straight line so it was smooth, it would be something like that dotted line. And that little red line there is equivalent of 6 hours buffer. So the idea that 6 hours buffer would actually smooth this out is ridiculous. So what's also interesting, this is the data from 5 countries where wind generation was actually sort of, stacked on top of each other. When you're seeing a peak, you often see the peak not just in one country, but like in several countries at once. So when one country has a peak, everyone has a peak. And when there's a lull, everyone has a lull, and they go for a couple of days. The trouble starts is when you start getting lulls close together and the grid has not had time to recover. That figure of 12 weeks is to accommodate for weather when we get sort of multiple spells of bad weather relatively close to each other. The grid needs 12 weeks of capacity to ride through that and then recover in time to be useful. So some of these peaks vary, and in this data set was up to 48%. In another data set I saw it was over 60. The size of the peaks or the size of the variations is dictating the size of the need of the buffer for wind. The United States Department of Energy got hold of my work in late 2021, and my results were very different to theirs. So they did an internal audit, and they came back and said, you're basically correct. And they asked me to look at this website, the PJM-RTO network in the United States. All this data's on their website, 100 million people. And what they found was I was correct. So they did a study for the numbers been assembled now for 2 years. Wind and solar underperformed for 4 to 6 months a year. And not only were the capacity factors low, but they were low points at precisely the seasonally worst possible times. So this was a difficulty. So, and in 2023, they had the same basic pattern. And so, and the variability in this data is enormous. So balancing one off against the other, like wind off against solar, is going to be really, really rough. It's going to create such power spikes and brownouts and blackouts if they were to try and do that. In practical terms, this is the information that I collected from the Global Energy Observatory. So solar voltaics were producing power 11.4% of the calendar year in 2018, and wind was producing 24.9. And I think engineering advances has brought that wind power up to 33% now. Even so, most of the time, these units are idle because they're subject to the weather. And one of the solutions that's been proposed is a 3 times build out for wind and solar. I did a study on that, took part in it with someone else. That 3 times build out is not enough. And even if you go to 8 times build out, it's still not enough because when these units stop producing, they stop producing everywhere. Okay, so this is the second part of the study where I was looking at once we've got the actual amount of power that we need to bring online, how many physical units do we need to deliver for the full system? How much steel, hydrogen, ammonia production is needed? And what is the metal content of each of the wind turbine units and each of the solar panel units and each of the new power stations? What battery capacity needs to be operating both in the EV fleet and stationary storage buffer, power storage buffer? What is the market share of the different chemistries involved using an IEA 2050 prediction? And given that, what is the metal content of each chemistry? And you sum all that together, what quantity of metals by each metal is needed? So I came up with this table of numbers. So the entire system, wind turbines, solar panels, electric vehicles, etc., all summed together, the primary difference, the biggest difference between them is the size of the stationary storage buffer. The pink is the 6 hours, which is what the establishment thinking believes, all the way up to 12 weeks, which is the blue, which is probably closer to the real number. So what I've actually sort of done is actually summed all the metals together and then quoted them like this. So let's take out copper. Oh, there's our global mining production. So that's the amount of metal we need for full system replacement, as in everything around us now is now non-fossil fuels, and this is global mining production in 2019. Why 2019? It's the last year of sensible data, because after that we had the COVID-19 pandemic supply disruptions and there's all these strange artifacts in the data. So let's pull out copper. Okay, in 2019, the global market produced 24 million tons, 24.2 million. If we were to do the 6 hour buffer only, which is ridiculous, but let's say we did, we could probably manage it because it's around a little under 12 years. But the moment we get out to say 28 days, we're talking hundreds of years. In this case, 745 years of production at the existing rate. The problem is we want to get it done by 2050, which is 25.5 years, where the practical answer is between the red and the blue, closer to the blue. Yeah, it's probably not going to go. All right, so what I did was I summed together, the obvious question is, can the mining industry now expand? All right, so open more mines, that's easy, right? This is the log scale on the left-hand side here. So we've got the pink, which is our 6 hours, all the way out to the blue, which is our 12 weeks. Now the hatched column here is all the metal in mineral reserves plus estimated mineral resources plus what undersea resources that we know of so far. So all the metal we've put together in the system we call planet Earth up against the amount of metal that we will need to keep us standing still in a non-fossil fuel world. And as you can see, if the real number's blue or close to blue, none of this is good enough. Now, some people find a log chart confusing. So here is the same data in a linear chart. And the right column is the grey is mineral reserves, the white is resources, and the black is what is known under the sea. Now, at this point, I like to point out that this is a crap plan. And we're required to take this seriously, because if we try and actually sort of do this, not only will it fail, it will cause us a lot of problems. Right, let's look at this a little further. What is the quantity of metal mined in the last 34 years compared to the amount of metal needed? What I'm really asking here is, can recycling deliver? If it hasn't been mined in the last 34 years, if we can't access it on like a waste heap somewhere, then there's nothing to recycle. So how much is actually out there? So this is copper. Between 1990 and 2023, globally, we mined 520 million tons of copper. And if we were to engage in the 12-week buffer, we need 34 times that historical amount. So if the past 30 years of mining was not enough, then recycling can't be the source. So here's nickel. Here's lithium. You hear a lot about lithium. Lithium's the answer. We're discovering lithium. Isn't lithium grand? Even at the 6-hour buffer, which is ridiculous, we need 24.6 times the last 34 years of production. So the idea that we're going to recycle our way out of this is not correct. There's cobalt. Again, similar signature, 312 times our historical volume. Graphite. Now this one I didn't really sort of see coming, but it turns out even though we've got a vast amount of graphite to work with compared to what we want now, we're going to need an enormous amount to deliver the batteries. Here's vanadium. So the idea of the vanadium redox battery. So what we need coming in is far in excess of what has been mined, and what has not yet been mined cannot be recycled. So what about the waste rock, the overburden? Right. So in Australia, Gavin Mudd has collected some really good data to show between 1934 and 2012, so talking 78 years, they actually, the Australian mining industry produced 2.8 billion with a B tons of waste rock as a consequence of copper mining. Now, assuming that same waste to ore ratio for 2012 and with each passing year it gets worse as grades going down, just for the 6-hour buffer, we would need 28 times that in, we would produce 28 times that in waste rock for the last 78 years. So the scale of this problem is enormous, far larger than existing thinking allows for. And if 12 weeks is the real number, we've got 1,792 times the volume of rock in overburden. So this would be environmentally disastrous. It's not going to work. And so what I was saying here is, instead of trying to force this particular solution, we should look at something else. So let's look at sensitivity. All right. So what I've done here is I have changed a parameter in the full calculation net. So the calculation outcome for the standard study was 48,939 terawatt hours. What would happen if we, for example, reduced the electric vehicle fleet by 50%? There was half the cars. Or if we increased the number of cars by 200%, and then we did the whole calculation again, what would this look like? Then there was trucks with hydrogen, maritime shipping. If we wiped it out by to 90, reduced it to 90% to 10% of what it is now. Steel production and ammonia production. Oh, okay, look at this. These figures are around the wrong way. Red is supposed to be steel and brown is supposed to be ammonia. So some of these labels are incorrect. I've got to fix that. If we reduce building heating by 50%, or if we looked at the conventional electrical demand, like what we're demanding electric now, but if we reduce that demand by 50%, or we increased it by 200 or 300%, like you're hearing conflicting things. Like on one hand, the power grid will be 3 times the size it is now by 2050. On the other hand, efficiency is going to take over and we're going to be a fraction of the size. And what would that look like? Then I did a very interesting study in degrowth and reconstruction. If we take the Club of Rome recommendations and we were to degrowth society, what would that look like? And then we also had to reconstruct everything really, really quickly. So it was a fast rebuild. All right, let's look at this. So here is our baseline. Going that this dotted line is 48,939 terawatt hours. And as we go along, you can sort of see how things change. So we reduce the EV fleet by 50%, 90%, or we're going to double it in size. Or if we increase the number of buses by a factor of 3, not a lot of changes. Trucks, well, there's a bigger change there, but again, nothing dramatic. If the rail network increased by 300% and they were hydrogen fuel celled, what would that look like? Maritime shipping. So if we reduced the maritime shipping by 90%, 10% the size of it is now, we're only reducing it by a couple of percent from that baseline. Ammonia. What's driving this is each of these tasks is relatively small and there's a lot of tasks together. There's only a few tasks that actually have much impact at all. Now, steel production. Steel production is now done with a hybrid system in a hydrogen atmosphere, and we're going to make that hydrogen. And making the hydrogen's the hard part. So we're going to reduce it by 90%. Or if we're going to rebuild society, and steel production is a proxy for industrialization. So if we're going to have like a really, really fast production of everything, and we're going to 5 times the quantity of steel that we're using now to rebuild everything and do it quickly, which is what the implications are of some of the proposals for the future. So building heating reduced by 50%, that was a very small amount. The reason that's here is I wanted a separation between the steel and the, this is reducing electricity demand by 50%, 90%, or if we increase it. So with the biggest swings, the black and the red, electricity demand or steel production. But if we're to reduce electricity demand, we're going to have to restructure society, thus more steel production. What was very interesting was the degrowth scenario, which involved a lot of steel production to rebuild everything. All the gains that were brought in by reducing society by quite a lot were really wiped out by all the construction requirements. All right, let's look at the same data, but now we're actually looking at metal content. So this is the amount of metal that we would need where to produce the amount of metal for this 48,939 terawatt hours. If we're going to move, how much percent change for all of these metals and the units of millions of tons. So changing the electric vehicle fleet didn't really change much in the scheme of things. I think we've got about 8 or 9% swings. The hydrogen fuel cell trucks, again, it did change things a bit, but not as much as you thought. 3 times the rail network. That didn't make much difference at all, which means we should probably think about doing it. Maritime shipping. So if we reduce that by, say, 90%, it made very little difference. Ammonia production. This is for fertilizer, but also as a fuel. Very little difference in the scheme of things. Steel production, that changed a few things. All right, especially when we went up to increase like a factor of 5. If we reduce energy demand, yes, that also made quite a serious swing. And if we increased energy demand, we had these bigger swings. So the big swings are associated with steel production or energy demand, which has implications for future planning. And there's the degrowth and rebuild. We can look at that in more detail later. So the second part of the sensitivity analysis. So we now know, before we were actually changing how much power we would need by making choices about things like vehicle size, fleet. But now that we're going to set the power, what if we had a change of, for example, solar voltaic panels increase in effectiveness by 200%. So instead of actually operating for 11.4% of the time, they're now operating for 22.8%. Or wind turbines became twice as effective. Like not just a little efficiency change of 1 or 2% here and there, but twice as effective. What would happen? If the global energy mix was entirely solar and wind, this should be solar and wind, 50-50 each. What would happen if we increased, so each of these are one change and we will do the entire calculation again to isolate that change. So what if we increase the percentage of nuclear in the mix? So 10, 20, and 30. And so 30% scenario zeta is the nuclear, the energy mix for the globe is now 30% nuclear. What would that mean? If there was a change in the battery market, if LFP batteries took over and made up of 80% of the global market share for everything, or solid state batteries came in and they took 80% of the market share. All right, let's look at that. Solar, 200% more productive, nothing. It did make a difference, but the difference is so small you can't really see it on this graph. And the same for wind. Or if all power was 50% solar, 50% wind, there's a 30% increase in the total amount of materials. Alternatively, if we took on a large proportion of nuclear, there is a 30% contraction. And that difference there, that run across there, that is actually a function of nuclear power is actually much more effective than wind or solar, coming down to the availability and the concentration of that power. If the battery market changed, like this is LFP batteries are 80%, and solid state batteries are 80%, that didn't make much difference at all. And the degrowth and rebuild scenario, that involved a 14% contraction of the total amount of materials. So what's happening here is the nuclear power plant fleet increases. That is the one change where you move off this and you move on to something else. And we're seeing a massive contraction in the amount of materials. That being said, I don't think this is enough. And here's why. Economic growth over the last the amount of copper mined by human society over the last 4,000 years, back to 4,000 BC, was 700 million tons. Now, according to projected economic growth, we're going to mine another 700 million tons in the next 22 years. Current reserves are 880 million tons. So we've got about 30 years of production. So we've got to find more stuff. Imagine if we wanted to load 6.1 billion with a B on top. This is 880 million. This is 6.1 billion just to manufacture one generation of renewable technology units around us. That is 8.8 times this historical quantity. It's probably not going to happen. Right, so scenario mu, what was that? So this is the limits to growth, Club of Rome idea, and plus a fast rebuild and restructure of society. Class 8 trucks are reduced by 50%, vans are reduced by 40%, passenger cars are reduced by 70%. So the transport fleet is about a third, something like a third of what it is now. Maritime shipping is reduced by 60%. Conventional electric power is cut by 50%. On the other hand, rail transport's increased by 300%. We're going to more communal transport. Buses are increased by 300%, and steel production has increased by 300%. So this last one down the bottom here, 300% increase in steel production, that is actually wiping out most of the gains achieved by everything else on this slide. And so here's how it looks. On the left, we've got the base case calculation, and on the right, we've got the degrowth scenario. So if we're not including steel, which is the red, we've got a 32.9% contraction of the existing system. The transport fleet goes from the way it is now to a much greater proportion of communal transport. So we've got, here's our scale here. All of this is coming out in the paper. So the numbers behind this are all sort of available. But what this is showing is if we're not going to use fossil fuels to rebuild our society, then we've got to use non-fossil fuel systems to do that, and they're not as effective. And if we want a fast rebuild, restructure of everything, we've got to pay the piper. So even at this massive reduction of society's footprint, this last little thing down the bottom here is really going to cost us badly. So what does all this mean? Current plans for after oil are not good enough. It's as simple as that. We're seriously underestimated the scale of the task. The green transition in its current form will not be feasible for all people and nations. The technology to store power in large enough quantities does not yet exist, and until it does, wind and solar are not viable as a large self-sufficient systems. As such, they cannot be the primary power source for the next industrial era. Hopes for future technology breakthroughs to somehow give us more commodity resources don't seem to consider the nature of the mineral resources that are left, and the current system has no idea of its dependency on minerals and does not consider long-term concepts like continuous growth in production against finite resources. Our society is energy blind and minerals blind. This suggests the green transition in its current form will not be feasible. Actually, is that said twice? It is too. Look at that. I've got a spare one. I'll have to fix that. All right. An attempt to expand the mining industry in such a steps change would be environmentally disastrous. Required quantities of metal far exceed known mineral reserves and resources. We do not have the time to explore for more and the quantities needed, even if they existed. Recycling cannot deliver the needed quantity of metals. There has not been enough mined historically to recycle, even if we could access it. Inevitably, it leads to the conclusion the existing renewable energy sectors and the EV technology systems are merely stepping stones to something else, rather than the final solution. So it's recommended that some thought be given to what that something else might be. So ecological reality and biophysical limitations will reassert itself for the first time in centuries. So, all right, what are we doing? Fossil fuels are being phased out. The green transition faces serious bottlenecks. Even if the green transition was successful, it still may not be strong enough to maintain the same capacity and flexibility that fossil fuels now give us. And so what might work? I'm now going to present to you what I call the purple transition. Now remember, these ideas are in relatively early stages and we still have to look at a few things and we still have to do some of the calculations involved. So this is a work in progress. What are we trying to do? We want electricity generation, transport and manufacture. We want reliable and consistent, stable in all weathers, power generation, all geographical regions, preferably in concentrated form, preferably with a low materials footprint, a long working life, designed to be recycled so when these units wear out, we know what to do with them. At the moment, we don't. Oh yes, a minimal waste plume with a very low environmental impact. That's the laundry list. Okay. At the heart of all of it, we need to reimagine where we get our raw materials from and energy. When we talk about, when we watch the 6 o'clock news, we are told all about the stock market, sometimes about technology, but that's about it. And it's sort of seen as an isolated thing, and that's actually the system that actually dictates reality. But what really happens is you've got a fourfold system where any given commodities you're looking at, it's not just minerals, it's the energy to extract those minerals, it's the technology to extract the minerals and then to use those minerals, and there's the economics of the whole system. And where there's one, you've actually got the other three, and if you're to do this properly, you actually can't separate them. And it's also recognized that all four of these aspects are harvesting feedstock from the planetary environment. So this is how we've really been all along, but we haven't really been managing the system as such. Our relationship between all four aspects and the planetary environment is changing. So we're required to change with all that. So the purple transition in summary goes like this. At the heart is a reimagined commodity sector, which I call the resource balanced economy. Around that, we've got thorium molten salt, an evolution of the nuclear sector, combustion of iron powder, ammonia-fueled ICE, and we're going to make batteries out of different chemistries. And they're all stitched together in a dynamic system. That system has the commodity sector and energy. Our energy resources, where we get our energy from and how we use it, is the heart of everything and dictates terms to everything else. So, all right, there's two sides of the equation. One is power generation and the other is what we use the power for. So we want transport, which at the moment is internal combustion, engine, petroleum, electricity and manufacture. We've got oil, gas and coal, and now nuclear. We want to wipe out petroleum. Okay, and now we've got all these new green technologies we're bringing online. Okay. Solar and wind are flagged as the next energy system for the future. We've got electric vehicles, biofuels, and hydrogen fuel cells. The electric vehicles have a limitation in batteries, as in the raw materials to produce enough batteries is the problem. That won't work. Biofuels the planet can only supply so much biomass, which means while biofuels have their place, they are not going to be the primary system. Hydrogen. Now, I'm actually proposing the hydrogen economy can proceed, but not the way in its current form. The limitations in storage and transport of a large quantity of hydrogen, we can do it in small quantities, but we don't really have the technology to do it in large quantities. And the problem is hydrogen is such a difficult gas to contain. It makes a lot of materials brittle and it escapes and it's flammable. So that's not going to work in its current form. Wind and solar, the buffer to manage intermittency is a problem. We can't store that amount of power for that long. We just don't have the technology for it. And our plans to do so can't really be scaled up. So that's not going to work. Hydro, all these other ones here, they have limits to expansion, as we can only put up so many more of these systems. We can't put up 20,000 new hydro stations across the planet because they can only go in certain geographical areas. Geothermal deposits are only also available in some places, not everywhere. Biowaste has the same problem as biofuels. There's limited biomass. Wave has its place. The units that generate power, though, they get knocked around in terms of maintenance in salt water, and also the number of units you need to actually make a useful contribution exceeds the actual coastline we actually have. Nuclear. Now, uranium scale nuclear can't actually expand fast enough to be useful. We're taking too long to build these stations. They're too big. They're also too complex, and there's concerns about the back end of the nuclear powered fuel cycle. However, there's a way through. What's also not discussed, and I haven't heard this anywhere, is what happens when we knock out coal. What happens to manufacture? A lot of our manufacturing systems need heat. Take away coal, and our options are limited. And so at the moment, if we stopped coal, then we lose most of our manufacture in an unplanned way and it just all stops. The first technology, internal combustion ammonia. Now, it's a mature technology, but there are a few things to ask here. The exhaust gas is a problem. We'll talk about that later, but apparently there's a catalytic converter system to manage that. Is that true? The pertinent question is, can we produce ammonia from seawater? And the answer is yes, if we're using heat to do it. The liquid fuel fission using thorium as the fuel, also known as molten salt, that can help us, and it's got the heat. So The third technology, or the fourth technology, is combustion of iron oxide powder to produce heat. So let's talk about these different systems. We'll do molten salt first. This is a report from 1972 that actually looked at this. It was a status report of outcome of several decades of research. The simple answer is it worked. This is what it is. So the nuclear fuel is in the form of thorium and sometimes uranium embedded in a salt, a fluoride salt, and it's put in the reactor. Then some of that salt is bombarded with neutrons, either from a uranium plug or a proton lamp. Some of that thorium is transmuted atomically to become an isotope of uranium, uranium-233, which is very hot. It heats up the salt turns liquid, and it starts to flow around the circuit. And heat is transferred from one tank to another, which then actually is used to turn water into steam, and steam turns a turbine, which generates electricity. What's interesting is you don't need to actually cool this with graphite rods. You don't need water to cool it. You do use water to control the actual temperature, but there are two systems that actually will stop this from overrunning. One is the Doppler broadening, Doppler broadening phenomenon, which if temperature gets too high, the reaction will cascade on top of itself and collapse. The second one is if the temperature gets too high, a freeze plug will melt and fuel drains out of the reactor to be dealt with separately. The fuel recirculates around this circuit, which means you can add fuel and take out fuel without actually stopping the reactor at all. It's a fundamentally different system. So this is the system that was actually tested in 1969 at Oak Ridge. It's a 7 megawatt system, 6,000 pounds of power generation without an issue. There is a system running now in the Gobi Desert in China. It's a pilot system, but it's now commercially selling power. So the East is already doing this, and we are being left behind. Right, so let's compare these two systems, the thorium system with uranium system. 1 gram of uranium or thorium of the right isotope, which is the key, can produce 24 megawatt hours of thermal energy. So let's look at uranium. So you start out, we're going to get 312 tons of yellow cake, and then we're going to convert it to uranium hexafluoride, enrich it where we actually want the isotope U235. That's the actual isotope we need, but it's only 4% of the fuel. And that goes into 36 tons of nuclear fuel rod assemblies. And we're going to generate 10,000 gigawatt hours over 1 year. And this is like a standard size generation 3 reactor. What's interesting is the waste that is generated is 96% of the mass that goes in. Most of the nuclear fuel is not used. And that's because the isotope that comes out is mostly U238. It's very hot, it's very radioactive, and some of that waste has to be stored for 100,000 years. And we've got about 19 kilos of the nasty stuff. But we're talking about 30 tons being generated. Do the same thing with the thorium system. Well, we're going to do is start with 290 tons of monazite sand. Already the system's smaller. We're going to make a thorium fluoride salt. We pour that into the top of the reactor. It runs. Now, when I first looked at this, it was the logic was between 1 and 5% of the fuel was not used, and it was actually sort of taken out as waste. But I've actually found a publication of a fuel mass balance around the Japanese Fuji U3 MSR system, 30 years of operation. And when you look at that mass balance, 0.08% of fuel is material that can't be used again and has to be stored as waste. So 10 kilograms is actual 11, if you round it up. 11 kilograms is actually what goes into waste storage. But that is also made of isotopes that are actually useful for the medical isotope industry. So it's possible you could reuse them again, or we could just store them for 300 years. They're classed as low-level waste. So what's interesting is this liquid fuel system can run with a uranium mix and can also, in some circumstances, consume spent nuclear fuel. We can run down the spent nuclear fuel stockpile. So this is Copenhagen Atomics. It's a group in Copenhagen that are actually sort of there's several groups that are actually looking at this. This is their design. I'm just going to move along. I'm running out of time. This is their full system. So they've got the reactor in the center. You've got your heat exchanger, and heat comes out here. There's like 560 degrees Celsius heat comes out. And they're using water on this side to actually control the reaction to make sure that heat stays in a tightly controlled bandwidth. So this is the full-size system. It's like a 40-foot shipping container. It arrives on a truck, and when it's installed, they put 50 years of fuel in it. This is me at the Copenhagen factory wearing a tie for the first time in 25 years. I'm standing in front of one of their test rigs. They've got a whole factory full of test rigs, and they're all testing one part of the system for QA QC to make sure that this technology is quite stable. And this is one half of the system. So this is the power reactor there, and this is the water testing system. So it is this right-hand side of this diagram. So each reactor is planned to produce 100 megawatts of thermal heat or 40 megawatts of electricity. So that system there is 40 megawatts of electricity. That's huge. It's a modular system, so you can fit several of them together to get whatever capacity you want. They're going to sell the electricity at 2 cents a kilowatt hour. So a plant that's producing, say, a 1 gigawatt of electricity will consume something like 800 kilograms of thorium-232 in salt form each year. So Copenhagen Atomics is planning to release this to the public in 2028. They will not sell the reactors, they will sell the electricity. So they will finance, build and own and operate these reactors for the customer. Right, so that brings us to, okay, so that's thorium. Now let's move on to heat in energy. Manufacturing consumes 54% of primary energy in a global industrial system, and usually in a concentrated form. And it's often required to be consistently and reliably supplied over a time measured in years. And the quantity is huge, 73% of coal, 37% of gas, and so on, 40% of electricity. So fossil fuel generation, heat generation was knocked out, we would lose the ability to do all this. And these are the sorts of things that we need to do. The left-hand column is temperature, and there are things like smelting of ore, melting of metal, making of cement. It all requires heat. And we need to be reliably producing heat over 1200 degrees Celsius for an extended period of time. So here is the non-fossil fuel systems that are quoted, and then here's the actual temperatures that they can get to. And it's really only the first three that are actually any good, and everything else is actually too small. Molten salt is down at 560, so the thorium reactor won't do it. Your normal nuclear reactor also won't do it. It's still too low. They've got a ceiling of around 850. So, and concentrated solar power, again, too low. So what does work? Well, biodiesel, ethanol, but we can only supply so much biomass. Good luck replacing coal. Hydrogen, but you've got to make the hydrogen. And how much hydrogen do you have to make to replace coal? That's where the whole thing is blown out. Electric resistance in the electric arc furnaces, that does work in some circumstances, but not all circumstances, and that puts extra pressure on the electric power grid. So it's really only those three. So what is proposed is the burning of iron powder. So this is a metal fuel to release the chemical energy. When you burn iron, it's like a coal replacement. You can get 2000 degrees Celsius. depending on the oxidation. So burn the iron powder, and then you can do things like produce hydrogen using the sulfur iodine cycle. And 800 degrees, that's not a problem. And after that, we've got all our industrial tasks. So 1 ton of iron powder creates 1.6 megawatt hours of fuel. So we've got an energy density of maybe 6 megawatt hours a cubic meter, where coal's 5. So it's actually better than coal, but you need specialist equipment to keep it going. Now, there's a number of questions here that need to be answered, and the work hasn't been done yet. Where it gets interesting is that iron powder can be recycled. Burn the powder, and pure iron powder goes to iron oxide, also known as rust. Right. So we can actually take that rust and convert it back to iron powder. One way to do it is put it into a hydrogen atmosphere or a supercritical steam a stream, like what comes out of a power station. The other way is electrochemical reduction, which requires electrical power to do it. How much electrical power? Don't know yet. And what is the actual energy balance to actually sort of take iron oxide and turn it back to pure iron powder? Don't know yet. How do the iron powders age? Like it's magnetic, which means it will aggregate, and some of the particles will now be too big. What do we do with that? Do we then put them into a grinding machine to knock them down in size? But that'll take energy. So do we recycle it all and do we just use more iron? All of these questions have yet to be answered. These are the 4 ways of doing it. So we've got producing iron powder from rust. You've got 2 ways to do it, with hydrogen and without. And then we've got burning that iron powder to produce heat and energy, dry cycle and wet cycle. So this is actually fairly standard chemistry. It really is just a case of working out the mass balance to see if this is economically sensible. There's a company called Metalot, again in Copenhagen. They've actually got proof of concept in 2020, and they're running a prototype in 2022 for a 100 kilowatt hour system. So the data's out there to see this. And if this works, this actually will make the whole idea of the purple transition pretty good. All right, the 4th technology is make batteries out of something else. This is not rocket science. This is the theoretical atomic combinations. Lithium ion is in the bottom left-hand corner. And so all of these are better. So the fluoride in your toothpaste can be used to make a battery. So the sort of materials we're after are all things like usually called industrial waste. So we've got sodium ion here, and we've got fluoride. I like the sodiums, the fluorides the better, but you can also use chlorine as well, chloride. Then you've got your zinc and sodium air batteries. Each one will have their place, I feel. The valuable part becomes processing and refining to something useful. It's not rocket science, but this idea is still getting resistance in the funding mechanism associated for research and development. They only want to fund lithium-ion chemistry. Ammonia. So this is ammonia-fueled ICE. Maersk shipping company, also in Copenhagen, is developing an ammonia-fueled engine for big ships. And when I was there, someone mentioned that they were running it for 3 or 4 months continuously to test the technology. The opportunities of this: ammonia can be stored and transported easier than hydrogen, but you've got to spend more energy to make the ammonia from hydrogen. So you've got an energy penalty. Technology is mature though. We know what we're doing. The challenges are: ammonia is toxic to plants and animals, and it's a gas at room temperature and pressure, so it needs to be stored. The burning of ammonia has nitrogen oxide as the exhaust, or several nitrogen species, and they're a problem. The next slide, which is looked at by Toyota, claims that there's a catalytic conversion system that actually manages that. I've yet to see it though. The real problem for me is an untuned engine will have unburnt ammonia coming out of the exhaust. And for that reason, I believe we will not see ammonia ICE in cities. Toyota has come along and developed a passenger car using ammonia ICE, but I don't think we'll see this in large cities due to the exhaust problem. What this does tell me, though, is this technology is quite mature. And so if you can make such a small engine, well, this brings aviation back online. Not a jet engine, but a turboprop certainly can be done. Right, So now we're coming to the end here. So electricity generation, we'll use all existing systems for resilience of the system. Wind and solar will have no buffer. Baseload power generation, system pressure and momentum will be done by your conventional uranium reactors that we've got now, but they're producing spent nuclear fuel. And that brings us to the liquid fuel fission using thorium as the fuel, the MSR system. I believe over time this will become the primary energy system if it works as we think it will. Short range transport, all our small passenger cars and everything will be a combination of electric vehicles and hydrogen fuel cells using sodium and fluoride batteries. We've got to expand the power grid to charge those batteries. The heavier vehicles, Class 8 trucks and what have you, they're all going to be hydrogen fuel cells, but we've got to make the hydrogen. If we can make that hydrogen by burning iron powder and seawater, we're back in business. But to do that, we need electrical power to recycle that iron powder fuel, and that comes back to a thorium reactor. Long-range transport, I can see ammonia-fueled ICE, so our long-range ships, aviation, and intercity rail. But it comes back to ammonia production, which needs hydrogen, which will work if we can use burning iron powder and seawater. But the key here is you decentralize the whole network. So instead of like a centralized place where we then store, it's all sort of done in small units all over the countryside. So the purple transition looks something like this. Electrical power generation from your thorium unit gives us electricity. One of those tasks is charging the EVs, which will be powered by sodium and fluoride battery chemistries. Combustion of iron powder will go to steel production and manufacture. We're going to produce hydrogen, which will fuel our hydrogen fuel cell fleet. Ammonia production, which will then fuel the ammonia ICE, which will do all our long-range transport. The thorium networks will actually help recycle the fuel for the iron combustion network. Now you're looking at a system, everything balanced against everything else. Thorium empowers the combustion of iron, and combustion of iron empowers the ammonia-fueled ICE. And so no one technology is the magic bullet, but everything working together in an integrated system might be useful. So what we're looking at here is a number of black swans are coming into land. Some of them are visible, some of them are not, some of them are useful, some of them will just break stuff. So that's the presentation. Thank you very much. Open the floor for questions.